What if I told you that right now, you might not be one person, not a metaphor, not a philosophical riddle, an actual, scientifically demonstrated fact, that cutting a single bundle of nerve fibers inside the human skull can create two separate streams of consciousness, in the same body, two minds, one skull. Split brain experiments. Can one body have two minds? Before we can talk about splitting the brain, we need to understand what holds it together. Your brain has two hemispheres, the left and the right. You've probably heard that. Left brain for logic, right brain for creativity. That's a massive oversimplification, but the two-hemisphere structure, that part is real. Now here's the thing. Those two halves, they don't automatically know what each other is doing. They need a bridge. That bridge is called the corpus callosum. It's a bundle of roughly 200 to 250 million nerve fibers, axons, connecting your left hemisphere to your right. Every second, billions of signals race back and forth across this structure. It is, in a very real sense, the great unifier of your mind. Take it away, and things get strange. 1b. What each hemisphere does. Here's the basic division you need to know for this video. Your left hemisphere controls the right side of your body. Your right hemisphere controls the left side, cross-wired. That's just how vertebrate nervous systems evolved. But more importantly for our story, language. In roughly 95% of right-handed people, and most left-handers too, language is heavily left-lateralized. That means the left hemisphere handles speech, reading, and most verbal reasoning. The right hemisphere, it's better at spatial tasks, holistic pattern recognition, and, crucially, it processes visual information from your left visual field. Your left visual field. Not your left eye. This is a critical distinction, and it's going to matter enormously in a few minutes. When you look straight ahead, everything to your left goes to your right brain. Everything to your right goes to your left brain. Normally, the corpus callosum shares this information instantly, so you experience one unified visual world. Cut that bridge, and each hemisphere only knows its half. 1c. Brief history of the corpus callosum. For most of medical history, the corpus callosum was a mystery. Early 20th century neuroscientists joked that its only function was to hold the two brain hemispheres together mechanically, like a piece of biological duct tape. Then came the 1940s and 1950s. Animal experiments. Ronald Myers and Roger Sperry at the California Institute of Technology began cutting the corpus callosa of cats and monkeys. What they found shattered assumptions. A cat with a severed corpus callosum could learn a task with one eye, say, pressing a lever for food. Cover that eye and test the other. The cat had no memory of the task. The information simply hadn't transferred. Two hemispheres. Two separate learning systems. One animal. Sperry won the Nobel Prize for this line of work in 1981, but the most dramatic experiments weren't on cats. They were on humans. And they started in a hospital in New York, with a neurosurgeon named Joseph Bogan, and a patient referred to in history simply as epilepsy. At its worst, it is a neurological catastrophe. For patients with severe, intractable epilepsy, where seizures cannot be controlled by any medication, the 1950s offered almost nothing. Seizures could happen dozens of times a day. Grand mal seizures, full-body convulsions, loss of consciousness, sometimes lasting minutes. The cumulative brain damage was devastating. Neurosurgeon Joseph Bogan had an idea based on those animal experiments. If epileptic activity spreads from one hemisphere to the other across the corpus callosum, what if you cut it? Stop the seizure from spreading. Contain the electrical storm to one half of the brain. It was a radical idea. Critics feared it would produce a mental vegetable. Some argued that severing the brain's great communicating bridge would fundamentally destroy the person. Their personality. Their unity of self. But W.J. was desperate. A World War II veteran, a former Army paratrooper who'd suffered a serious head injury, his seizures had become unmanageable. He agreed to the procedure. In 1961, Bogan and Philip Vogel performed the first complete commissurotomy on a human patient, cutting the corpus callosum entirely. And to almost everyone's astonishment, WJ seemed completely normal. He could hold a conversation. He recognized his wife. His personality was intact. His seizures were dramatically reduced. He walked out of the hospital looking for all the world like a man with a whole, unified mind. But Roger Sperry suspected something more was happening beneath the surface. And so he designed a series of experiments that would change neuroscience forever. Here's the brilliance of Sperry's approach. The human eye moves. If you flash an image on a screen, the eyes dart around and both hemispheres receive the information. To isolate each hemisphere, you need to present information so briefly that the eyes can't move, typically under 200 milliseconds, about a fifth of a second. Flash and gone. Sperry had his patients fix their gaze on a central point. Then he'd flash images to the left or right of that point. Left of center, right hemisphere only gets the information. Right of center, left hemisphere only. And beneath the table, hidden from view, objects were placed for patients to feel with either their left hand, connected to the right brain, or their right hand, connected to the left brain. Simple setup. Explosive results. Flash the word apple to the right visual field. It reaches the left hemisphere, the language hemisphere. The patient reads it aloud without hesitation. Apple. Normal. Now flash the same word to the left visual field. It reaches only the right hemisphere. Ask the patient, what did you see? Nothing. I didn't see anything. But then, ask the patient to reach under the table with their left hand and select, by touch alone, the object that matches what they saw. The left hand, controlled by the right hemisphere, reaches out, and picks up the apple. The right hemisphere knew. It saw the word. It recognized it. It guided the hand. But it could not speak. It had no access to language. So to the verbal, conscious left hemisphere, and to the patient, nothing had been seen. The right brain knew something the left brain didn't. And the left brain, the one doing the talking, the one saying, I didn't see anything, was not lying. It genuinely had no idea. Two minds, one body, one unknowingly reporting the other's experience. Let's go deeper. Because it gets stranger. Sperry and his student Michael Gazzaniga, who would go on to become one of the most celebrated neuroscientists of the 20th century, began exploring not just what each hemisphere knew, but how each hemisphere responded emotionally and aesthetically. In one series of experiments, they created chimeric faces. Take a photograph, cut it down the middle, combine the left half of one face with the right half of another. Flash this composite image to the split-brain patient, centered on the fixation point. Animation, chimeric face construction. Half smiling, half neutral. Now here's the result. Ask the patient to verbally describe what they saw. They described the right half of the image, which reached their left hemisphere, their language brain. They might say, a neutral face, slightly blank expression. But ask them to point to the matching face from a set of photographs, and they point to the picture that matches the left half of the image. The half their right hemisphere saw. Two different faces, two different descriptions. Both from the same person, looking at the same image, at the same moment. And when asked to rate the faces for attractiveness, the right hemisphere, the one guiding the pointing hand, consistently chose differently than the verbal left hemisphere. Different aesthetic judgments, different preferences. From the same brain. At the same time, here's one of my favorite stories from this era of research. During one experimental session, researchers flashed a photograph of a nude person to the right hemisphere of a female split-brain patient. She began to laugh and blush, clearly reacting emotionally. But when asked what she saw, she said, nothing, just a flash of light. She was experiencing an emotion she couldn't explain. Her right brain was reacting. Her left brain, which had no idea what had caused the reaction, was genuinely confused by her own laughter. The right hemisphere felt something. The left hemisphere experienced the mysterious emotion without knowing its source, and started confabulating, making up an explanation. Maybe she felt briefly embarrassed for no reason. Maybe the experimenter said something funny. This phenomenon, the left brain making up stories to explain behaviors and feelings it didn't cause, would become one of the most philosophically charged discoveries in all of neuroscience. We'll return to it. Some split-brain patients develop a phenomenon dramatic enough to have its own name, alien hand syndrome. Imagine you reach out with your right hand to button your shirt. And your left hand, seemingly of its own will, reaches up and starts unbuttoning it. You didn't tell it to do that. You can't stop it easily. Your left hand has its own agenda. In one documented case, a patient would pick up a book with the right hand, and the left hand would put it down. The left hand, controlled by the right hemisphere, seemed to disagree with the right hemisphere's choices. In another dramatic case, a man's left hand would grab his wife during arguments. His left hand, quite literally, acted out his unconscious aggression while his verbal self, his left hemisphere, denied any hostile intent. This isn't metaphor. This isn't someone being manipulative. The motor system of one hemisphere was acting against the expressed wishes of the other. Two wills. One body. Researchers wanted to go further. What would happen if you could sustain one hemisphere isolation, not just for a fifth of a second, but for extended periods? Aaron Zadel developed a special contact lens, the Z-lens, that allowed researchers to restrict visual input to just one hemisphere while the patient's eyes moved freely. This opened up more extensive testing. What emerged was remarkable. With just the right hemisphere receiving information, patients could still understand language to a degree. Right hemisphere had a vocabulary of perhaps a 10 to 12-year-old's level. It understood nouns and simple sentences, but it had almost no ability to produce speech. It could point, it could select objects, it could make gestures, but it could not say a word. An entire hemisphere of the human brain, processing sensory information, understanding language, experiencing emotion, making decisions, completely mute. What would it be like to be that hemisphere? To experience and understand but never be able to say a word? Meanwhile, other neuroscientists were developing a parallel tool for exploring hemisphere dominance, the WADA test. Before brain surgery for epilepsy or tumor removal, surgeons need to know which hemisphere controls language for that specific patient. Knock out the wrong one during surgery, and the patient might wake up permanently unable to speak. The WADA test involves injecting sodium amobarbital, a fast-acting barbiturate, into the carotid artery on one side. This temporarily puts one entire hemisphere to sleep for a few minutes. The other hemisphere stays awake. Surgeons can then test language function in isolation. What patients describe during a WADA test is extraordinary. Some report feeling suddenly depersonalized, like they're half asleep, half present. Some report emotions fluctuating wildly as the dominant hemisphere loses control. Some experience a profound, eerie blankness. It's a brief, medically necessary window into what it might feel like to have one hemisphere taken offline. And by nearly every patient account, it feels profoundly wrong. Like half of you has temporarily stopped existing. Michael Gazzaniga spent decades working with split-brain patients after his time with Sperry. And from those decades, he built a theory that may be one of the most important, and most unsettling, ideas in cognitive science. He called it the interpreter. The left hemisphere, Gazzaniga argued, is not just a language processor. It is a storyteller. Constantly, automatically, compulsively. When the left hemisphere notices itself doing something, or feeling something, that it didn't consciously decide to do or feel, it doesn't say, "I don't know why." It makes something up. It constructs a narrative. It finds a cause, even if the cause is entirely fabricated, and it believes the story, completely. Gazzaniga demonstrated this with a famous experiment. He simultaneously showed a snow scene to a split-brain patient's right hemisphere and a chicken claw to the left hemisphere. Then he asked the patient to point, with both hands, to related pictures from an array of cards. The right hand pointed to a chicken. The left hand pointed to a shovel. Both correct, The left hemisphere saw the claw and associated it with chickens, the right hemisphere saw snow and associated it with shovels. Then Gazaniga asked, "Why did you point to those things?" The patient thought for a moment and said, "Oh, the chicken claw goes with the chicken, and you need a shovel to clean out the chicken shed." The left hemisphere had no idea why the left hand had pointed to the shovel. It hadn't received the snow scene. But it observed the behavior and instantly invented a plausible explanation. The story was false. The confidence was total. Gazaniga's conclusion was stark. The experience of being a unified self, of having reasons for your actions, of being a coherent narrator of your own life, may itself be a story that the left hemisphere tells. A confabulation. A narrative constructed after the fact to explain behavior that arose from processes the conscious narrator never controlled. This is where the split brain experiments stop being about a rare surgical procedure and start being about everyone. Because the question they raise is fundamental: what is consciousness? The standard intuitive model is something like this. There's a you somewhere in there, an observer, a decision maker, a unified experiencer, and your brain is the instrument that you use to navigate the world. Split brain research challenges that model at its foundation. If you can divide the brain and get two independent streams of awareness, each perceiving, remembering, desiring, acting, then which one is you? Is either of them, are both? Philosopher Thomas Nagel tackled this directly in his 1971 paper, Brain Bisection and the Unity of Consciousness, one of the most cited papers in all of 20th century philosophy of mind. Nagel concluded that the split brain cases present a genuine logical puzzle that none of our existing concepts of personal identity can solve. We want to say there's one person in the chair, but the experimental evidence suggests there may be two distinct streams of experience. Neither description fully fits. Neither can be comfortably dismissed. We simply don't have the philosophical vocabulary to describe what a split-brain patient is. There's a related puzzle called the binding problem. It's one of the deepest unsolved questions in neuroscience. When you look at a red ball rolling across a floor, your brain processes color in one region, shape in another, motion in a third, the sound of it rolling somewhere else entirely. These are distributed, parallel processes happening in widely separated brain regions. Yet you experience one unified object. One red ball, moving, making a sound. Not a collage of separately processed features. A unified thing. How does the brain bind all this disparate processing into a single unified perception? Nobody really knows. Various theories have been proposed. Synchronous neural oscillations, thalamic gating, global workspace theory, but none is universally accepted. The binding problem remains open. Split brain research sharpens this problem dramatically. If the corpus callosum is severed, the binding appears to break, at least partially. The right hemisphere has its red ball, the left hemisphere has its red ball, but they may not be sharing notes. Unity of consciousness may not be a fundamental feature of mind. It may be something the brain actively constructs, and something that can be broken. Here's the thought that may keep you up tonight. Even in a normal, intact brain, with a fully functioning corpus callosum, the two hemispheres are not perfectly synchronized. They process information differently. They have different strengths, different emotional registers, different cognitive styles. Research suggests that in normal people, the left hemisphere still confabulates, still makes up stories for behaviors that arose from nonverbal, non-conscious processes. We just can't see it as clearly because the information is being shared back and forth, blending the stories together into something that feels coherent. The self you experience, the unified narrator of your life, the I that seems to exist behind your eyes making decisions and having experiences, may always have been, to some degree, a construction. A post hoc explanation. A story the brain tells about itself. Split brain patients just make the seams visible. The original split brain patients, the ones who shaped a generation of neuroscience, are gone now. WJ died in 1995. The cohort studied intensively by Gazaniga and his colleagues has mostly passed. But split brain research hasn't ended. If anything, the questions are sharper than ever. And new tools are making it possible to probe them in ways Sperry could never have imagined. Functional MRI, fMRI, allows researchers to watch blood flow in the brain in real time, with millimeter-scale precision. It's possible now to watch, in a living patient, exactly which brain regions activate when each hemisphere processes information independently. And the images are striking. The two hemispheres of a split-brain patient do indeed activate independently for many tasks. No cascade across the callosum, no shared activation. Two separate patterns of activity, simultaneously, in one skull. In 2017, neuroscientist Jair Pinto and colleagues at the University of Amsterdam published a paper that genuinely shocked the field. They found that split-brain patients could perceive and respond to stimuli in both visual fields simultaneously, not just one at a time as the classic model suggested. Using a task where patients had to detect or discriminate visual stimuli while ignoring distractors, Pinto found evidence of what he called unified perception, the ability to perceive a unified scene even without a corpus callosum. This seemed to contradict decades of established understanding. How could a brain with no corpus callosum perceive a unified visual field? The answer, Pinto and colleagues proposed, is that the corpus callosum is not the only route for cross-hemisphere communication. Subcortical structures, pathways through the brainstem and thalamus, which are beneath the cortex and not cut by commissurotomy, may provide a second, parallel communication channel. The split brain, it turns out, is not as split as we thought. The communication is degraded. The integration is impaired. But it's not zero. This doesn't resolve the philosophical questions. Even if some low-level perceptual integration persists, the dramatic dissociations in higher cognition, in memory, in verbal reporting, in goal-directed behavior, remain real and well-documented. But it complicates the story considerably. Corpus callosotomy is still performed today, though less commonly. Improved anti-epileptic medications and more targeted surgical options, like laser ablation of small seizure foci, have reduced the need for complete commissurotomy. When it is performed today, it's often partial, cutting only the anterior portion of the corpus callosum, or only the posterior. This produces more subtle effects, and studying these partial split patients is helping researchers understand which fibers in the corpus callosum carry which types of information. Some patients born without a corpus callosum, a condition called agenesis of the corpus callosum, develop without the dramatic dissociation seen in surgical patients. Their brains appear to compensate, developing alternative connectivity routes. This suggests remarkable plasticity. The brain, given time, can partially work around the absence of its great bridge. But surgical split-brain patients, whose brains had decades to build connections across the callosum before it was cut, show much more dramatic effects. The brain has learned to rely on a road, and then the road is suddenly gone. People born without a corpus callosum, a condition affecting roughly 1 in 4,000 people, represent a fascinating natural experiment. They often have remarkably mild symptoms. Some are never diagnosed. Some show subtle difficulties with complex reasoning tasks, with social cognition, with integrating information across domains. But many live completely normal lives. Yet when researchers test them carefully with the same lateralized visual field paradigm Sperry used, they often show the same hemisphere dissociations. The left hand doesn't know what the right hand is doing, literally. They've just found ways to work around it, to compensate, to approximate unity from divided components. Which raises a disquieting possibility. Maybe what we experience as the unity of consciousness is always, to some degree, an approximation. A very good one, in a healthy brain. But an approximation nonetheless. The philosophy of what makes you you, through time and change, is one of the oldest philosophical problems. John Locke argued that personal identity is constituted by continuity of memory. Derek Parfit argued that identity itself is less fundamental than we think, that what matters is psychological continuity, and that strict identity may not even be coherent. Split-brain cases put flesh on these abstract bones. Consider, after commissurotomy, the right hemisphere and left hemisphere develop separate memory traces for the same events, because they're processing them differently and can no longer fully share. Over years, the two hemispheres can accumulate partially divergent memories of the patient's own life. Whose memories are those? If your left hemisphere remembers your wedding differently than your right hemisphere does, because each was processing different aspects of that day's sensory experience, and neither fully knows what the other encoded, what is your memory of your wedding? The self as a single unified entity with a single coherent memory trace may be, even in normal humans, a convenient fiction. Can one body have two minds? The honest answer, 50 years into serious split brain research, is, it's more complicated than yes or no. Yes, cut the corpus callosum, and you produce two measurably independent streams of cognition. Two systems that can perceive different things, remember different things, want different things, and act on those wants, sometimes against each other. But also, those two streams are not entirely independent. They share a body, they share a face, they share a history. Subcortical pathways continue to pass low-level information, and whatever the right hemisphere feels, the left hemisphere feels the feeling, even without knowing its cause. So maybe the question isn't can one body have two minds? Maybe the better question is, what made us think one body ever had exactly one? Right now, as you watch this, your brain is doing thousands of things you're not aware of. Your right hemisphere is processing the left half of this image. Your visual cortex is filling in your blind spot with invented data. Your motor cortex started preparing your next movement before you consciously decided to make it. The you that feels like the observer, the one sitting behind your eyes watching your own life, is a construction. A useful one, a convincing one, but a construction assembled by a massively parallel, distributed system that is far larger, far more complex, and far less unified than the self it generates. The split brain experiments didn't create a puzzle where there was none. They revealed one that was always there, hidden behind the seamless performance of a brain doing its job so well we never noticed the seams. Roger Sperry wrote, near the end of his career, each hemisphere is a conscious system in its own right, perceiving, thinking, remembering, reasoning, willing, and emoting, all at a characteristically human level. Each hemisphere. A conscious system. In its own right. He wasn't speaking loosely, he meant it literally, and 40 years of subsequent research suggests he was right. Which means that somewhere in the history of surgery, in the cases of WJ, and the dozens of patients who followed, something extraordinary happened in an operating room. Not just a treatment for epilepsy, not just a clever neuroscientific experiment. A mind was divided, and both halves lived on. If you found this as fascinating and unsettling as I did, there's more in the description. Roger Sperry's original papers, Gazaniga's book The Consciousness Instinct, Thomas Nagel's essay, all of it worth your time. Thanks for watching.